Hello, everyone, and welcome to Signals, Systems, and Signal Processing with Wolfram U. The topic of this lesson is continuous time Fourier series. In this lesson, we'll introduce continuous time Fourier series and show how they play a very important role in the study of linear and time-invariant systems, or LTI systems. We will see in detail that LTI systems have this property where sinusoidal inputs result in sinusoidal outputs. Furthermore, we'll see that for a large class of signals, we can represent these signals as a linear combination of sinusoidal signals. And so for LTI systems, where we're interested in finding the system's response or basically the output of the system, we can think of the output as simply the superposition, a linear combination of the individual responses to each of these input signals. Let's start with the first property that we just mentioned. Having an LTI system with the impulse response h of t, consider a sinusoidal input signal x of t of the form e to the power j omega t. Now we can find the output signal y of t by convolving the signals h of t and x of t. Starting with the convolution integral and replacing x of t minus tau here with its value and simplifying, if we call this integral h of j omega, it's a complex value. This is provided that this integral exists, of course. The output then can be written as shown here. What we have obtained here is that the output is the input signal, the complex exponential e to the power j omega t, scaled by some constant value, h of j omega. In other words, for LTI systems, sinusoidal inputs result in sinusoidal outputs. Or if you recall from linear algebra, we call such signals or functions the eigenfunctions of the system. Let's look at the other property of sinusoids that we mentioned in the introduction. A large class of signals, namely periodic signals, can be written as a sum of sinusoidal waves. These waves will be harmonically related, and that means that their frequencies are integer multiples of a single frequency, which we call the fundamental frequency. This representation, or the summation, is what we call the Fourier series. Before going over the exact definition, let's look at an example. Here, SKTs define an infinite family of simple sine waves, S1, S2, and so forth. They are harmonically related, and their fundamental frequency is 2 pi radian per second. Let's use the Wolfram language and plot the three members of this family, the family of sine waves with frequencies 2 pi k, for k equal to 1, 3, and 5, and see how they change over time. Also, let's look at a scaled version of the three sines. This is how a linear combination of these sinusoids change over time. And note that this summation produced a periodic signal. Now let's look at another example with audio signals. On a modern 88-key piano, the frequency for any key n is given by the expression indicated here. Now let's say for the key number 52, which is the note C5, the frequency will be the value shown here. If we consider the family of harmonically related sinusoids with this value f of 52 as the fundamental frequency, the family can be represented by SKs as given here. Using the Wolfram language, we can create, play, and listen to the sound of this synthesized piano key, a linear combination of, let's say, the fundamental sine wave and its three lowest order harmonics, as shown here, with some scaling parameters. Comparing this sound with the actual recording of the C5 key, you can see that they're pretty close. Once again, we showed that a signal here, an audio signal, could be represented by a linear combination of sinusoids. Now, what we call the synthesis formula gives the definition of the complex Fourier series, which is a representation of a periodic signal x of t in terms of a linear combination of harmonically related complex exponentials with the form shown here. The quantity t denotes the period of the signal x of t, and 2 pi over t is the fundamental frequency of the signal. The coefficients ck are called the complex Fourier series coefficients of the signal x of t. And these coefficients for the periodic signal x of t are obtained using the analysis formula as indicated here. The Fourier series as we define them will not always exist. For the Fourier series to exist, the coefficient ck's must be finite. This is guaranteed if the periodic signal x of t has finite energy over a single period. In other words, the integral shown here must be finite. These are some examples of signals for which the Fourier series exists. And Fourier series may not exist for signals shown here. In these cases, the number of discontinuities or the number of maxima and minima, as you see, is not finite. And so the integration in the definition of Fourier series coefficients will not converge to a finite value. Now that we have the definition and the condition for existence of the Fourier series, let's look at an example where we would like to obtain the Fourier coefficients of the square wave shown here. Using the Wolfram language, the Fourier coefficient function can be used to obtain the Fourier series coefficients. The Fourier parameters option is used to match the analysis formula as we defined it here. The second parameter is the fundamental frequency 2 pi over t, where t is the period of the square wave, which is 1. So we have 2 pi. Let's look at a few of the Fourier series coefficients ck's for k going from -5 to 5. If we were to obtain these values by hand using the analysis formula, replacing t with 1 and x of t with 1 for t between 0 and 1/2, the integration can be simplified as shown here. Evaluating the integral and replacing the term e to the power minus j pi k with minus y to the power k, the coefficients can be expressed as indicated here, which means that C0 is 1/2 and the rest of the coefficients for odd values of k are 0 and for even values of k are expressed as shown here, which matches the results that we obtained using the Wolfram language. As another example, let's find the Fourier coefficients for the signal x of t given as sine of 2 pi t. Obtaining the Fourier series coefficients using the Wolfram language, we replace x of t with sine of 2 pi t and the fundamental frequency by 2 pi. And the coefficients are given as shown here. Now, to find these coefficients by hand, notice that since x of t is a sinusoid itself, instead of applying the analysis formula, we could just use the Euler's identity and rewrite x of t in terms of a sum of complex exponentials as shown here, which is what we want to obtain for the Fourier series representation. Now, comparing this expression with the Fourier series synthesis formula, let's look at the expanded version. We get that the coefficients are as listed here. Again, the same results as obtained by the Wolfram language. Since Fourier series coefficients are typically complex, it is common to plot their magnitude and their phase, or the real and imaginary parts of each of the components. For the components obtained in the square wave example, we see how the magnitude ck and phase of the coefficient ck change over a range of values of k here. We can also plot the real and imaginary components of the Fourier series coefficients as shown here. So far, in the earlier examples, we focused on finding the Fourier series coefficients using the analysis formula. Once we have these coefficients, the synthesis formula gives us the signal in terms of a linear combination of harmonically related complex exponentials. A real-valued periodic signal x of t is simply a finite or infinite linear superposition of scaled harmonic-related complex exponentials. In the case of the two previous examples, C1 and C-1 returned a sine wave, and coefficients C0 and Ck's for non-zero values of k gave a square wave with period 1. Now, if we consider the finite length version of the synthesis formula, as shown here, we can get an approximation of the signal. For example, for a centered square wave, the coefficients using the Wolfram language can be obtained as shown here. And a synthesis of the square wave with m equal to 3 will be this expression, as indicated here. It gives us an approximation of the square wave. For different values of n between 1 and 17 here, you can see the approximated signal. As m gets larger, the approximation becomes more accurate. However, if you pay attention, you can also observe a very important behavior called the Gibbs phenomenon, where we have this ripple effect near the discontinuity points of the signal. It is well known, as you see here, that the maximum magnitude of the ripple, also known as overshoots and undershoots, remain constant and independent of the order of approximation m, with a value roughly equal to 9% of the jump discontinuity. The average power of a signal x of t is given by the Parseval's relation for continuous time Fourier series. For the ideal square wave with period 1, for example, the average power will be 1/2. And so for the approximation signal, the power can be expressed as indicated here. Let's look at the average power of the approximation error for different values of m ranging from 1 to 51. The good news here is that the average power of the approximation error is guaranteed to diminish as we increase the value of m, or the number of the coefficients. In summary, in this lesson, we saw that sinusoidal inputs result in sinusoidal outputs, or they are the eigenfunctions of LTI systems. Also, periodic signals can be represented by finite or infinite Fourier series expansions. We went over several examples evaluating the analysis formula and the synthesis formula for Fourier series.